Hello everyone and welcome to lecture 6 of our course. Today we will talk about Newton's method for unconstrained nonlinear optimization. This is chapter number 3 from our textbook Practical Methods of Optimization by Roger Fletcher. So let's start. Newton's method is a method which uses both gradient and Hessian information for finding the next iterate in nonlinear unconstrained optimization. So recall that in steepest descent and line search we were using only the gradient information to find the direction and then some line search to find the step length. Newton's method, on the other hand, finds the direction and the step length together. There are no two steps here. So the method is as follows. While not converged, find the correction term. So we are not going to find direction and step length separately. We will just find the difference to the next point. So in the language of previous chapter, we will find alpha times s by solving a small system xk plus 1 is going to be xk plus alpha s and k equal to k plus 1. So let's see how this works. So recall the Taylor series approximation for any given function which is differentiable and smooth. F of x plus alpha times s is nearly equal to the function value at the previous point plus alpha s transpose gradient of f at the previous point plus a second order term which relies on the Hessian of f at the previous iterate plus some other higher order terms which we are going to ignore in this approximation. So since we have an approximation, we will be ignoring all the other terms. So So let's change the notation slightly and use a short notation for gradients and Hessians, and also this alpha times s. So we will say delta is equal to alpha times s. So this is a vector. So this delta includes both the step length as well as the direction in which we are moving. We can use g, small g, in place of the gradient, and capital G in place of the Hessian. So my approximation formula becomes fxk plus delta transpose gk plus half delta transpose capital GK into delta. And this is the notation we are going to use in this chapter. What the Newton method tries to do is take this model of f, and this is a quadratic model, as there are some linear terms and some square terms. So what Newton's method does is try to minimize this quadratic model and just go to the solution of that model. So what we do is find the minimum value of this quadratic model. So minimize over all possible delta fxk plus delta transpose gk plus half delta transpose capital GK delta. So in this optimization problem, fxk is known, gk is also known, and capital GK, they are all known. And the only variable is delta. And delta is a vector, so this is a multivariate optimization problem. In one dimension, in 1D, a quadratic function may look like a bowl, or like this. So but in higher dimensions, it may not have a minimum or max. Also, it may have saddle points like x1, x2. But at least in one dimension we can see that if somebody says here is a quadratic function and what is the minimum values, this minimum value can very well go to minus infinity. In case of a nice quadratic function like this, we know that the minimum would be unique and globally valid. So so in higher dimensions, whenever G is positive definite, when G is positive definite, matrix, then we have a minimum value or solution, and not just this geometric intuition. We have seen this in the previous chapter as well, when we wrote about sufficient conditions for finding a minimum or sufficient conditions for a local minimizer of function. So this is a sufficient condition. So whenever G is positive definite, we are quite confident that at least we will be able to find a delta by minimizing this function. Okay, so let me just write it here. Nice delta when G is positive definite. Delta star.